I've known Lucy for a very long time, and we're small molecule spectroscopists, among other things. She is many other things than I am. But so let me just give a little biographical history. She got her bachelor's at Rice, a PhD with Rich Senkley at Berkeley in 1984. She did a postdoc at UMass in the radio astronomy lab, and from 1988 to 96 she was at Arizona State University, and then from 96 on she's been at University of Arizona. She's in the Department of Chemistry and Biochemistry. She's also in the Department of Astronomy. She's the director of the Arizona Radio Observatory and director of the Kitt Peak 12-meter radio telescope. She is one of the world experts in microwave technology, and she also does really beautiful spectroscopy of metal-containing molecules. The title, Heavenly and Earthly Rotational Spectroscopy of Transient Molecules from the Microwave to the Terrace Region. Lucy.
Thank you, Bob. First of all, it's great being here, and I love to talk about small molecules, and that's pretty much what we'll do with the purpose of this talk. And for the course of this talk, and many applications of rotational spectroscopy. So I do pure rotational spectroscopy, and one might wonder what the motivations are. One of the biggest motivations to do rotational spectroscopy is to establish accurate monomeric solvent-free molecular structures. If you really work hard enough with isotopic substitutions, you can determine bond lengths of 0.005 angstroms and angles to less than half a degree. And rotational spectroscopy is the nice result that you can establish electronic states. And for many of the metal molecules we've done in the past, they weren't sure what the ground electronic state was, and the rotational spectra will tell you. And through examination of fine and hyperfine interactions, which we easily measure with rotational spectroscopy, we can get some bonding properties, and all of these serve as benchmarks for theoretical calculations, particularly important for things with transition metals. And rotational spectroscopy also allows you to investigate chemical reactivity in several different ways. It's a beautiful illustration of quantum mechanics. And it's another excellent example of what I call precision science. I mean, these days there's a lot of measurements that are done that are not reproducible, and the nice thing about rotational spectroscopy, if you do it right, it really gives you precise measurements that can be duplicated by other people. And of course, this precision science has been exploited by other fields, particularly those that do remote sensing, atmospheric science for one thing. And of course, most importantly, in my case, rotational spectroscopy has been the foundation of molecular astrophysics. Without rotational spectroscopy, they never would have discovered the molecules that they continue to discover out in space, and it's the most important tool for radio and millimeter wave astronomy. And it was the impetus for building this large radio telescope called the Atacama Large Millimeter Wave Array, or ALMA. This is the most expensive astronomy project in the history of the National Science Foundation. It basically is 50 telescopes used to make images of rotational spectra of molecules. Okay. So without rotational spectroscopy, we never would have built ALMA. And of course, this sort of talk can't go on without just a list of the known interstellar molecules. The ones I've worked in are in blue, but you can see there's a lot of diatomic species. We've made a lot of progress looking at metals and phosphorus containing ones, a lot of things with carbon. And perhaps the most exciting result recently has been the discoveries of C60, and in the past few months, C60 plus out in interstellar space. So you can see you're really running the gambit from a few carbons, maybe 11, 12, 13 carbons, to things with 60 carbons. And we don't really know what's in between, which is one of the major questions for spectroscopy and astronomy. And the other thing is about 90% of these molecules were identified by their pure rotational spectrum, and so that's been a big application, as I said, of rotational spectroscopy. Now, another interesting thing is that because people have been studying molecules out in interstellar space, first thing is no one ever thought molecules would be out there. And up to about 1970, the classic conclusion of most astronomers was there may be a few diatomic species, but nothing else. But since that time, our view of the molecular content of the galaxy has risen from less than 1% in 1970 to a few percent in the 1990s. And now they estimate that over 50% of the material, at least in the inner 60% of our galaxy, is molecular in nature. So things have really changed over the past 40 years. And like I said, we have some interesting organic sort of smaller molecules, and now we're up to C60. And one wonders where the molecules are with between about 12 and 59 carbon atoms. And that's something that the future will find out. And the other interesting thing is they're finding molecular material in the most extreme interstellar environments. And a striking example of this are what astronomers call planetary nebulae. They look like this. I'm sure you've seen bright and pretty pictures of them as posters and so forth, but they're the final stage of most stars when they die. They basically lose almost all their initial mass. It flows away from the star. The star becomes a white dwarf star, which is a hot ultraviolet emitting star, and it ionizes the material that's flown away from the star, creates these bright, often multipolar nebulae. And for the past 40 years, people said, oh, there's too much ultraviolet radiation for molecules to be present there. But now we've been studying them, and they're quite molecule rich. And that's work of one of my students, Debbie Schmidt, in the astronomy department. That's a very new and interesting avenue. So the more we look, the more molecular material we find in the more extreme environments. And I think that's a trend that's going to continue. Okay, so one can no longer, this is more astronomy type stuff, can think of, oh, we just go detect this molecule here, we detect this molecule there. The past 40 years have shown there's actually a molecular life cycle that occurs out in interstellar space. It starts, let's say, with dying stars. They throw material away. From them, molecules form. They last as the star becomes a white dwarf. Molecular material is now deposited into the interstellar medium to form these very diffuse clouds, which collapse into dense clouds. And in dense clouds, stars and solar systems form. And then the process starts again. And some of this material actually ends up on planet surfaces. But the whole point is the molecular material now is being recycled to the interstellar medium. So the chemical timescales are no longer that of an individual object, but the chemical timescale of the lifetime of the galaxy, which is about 10 billion years. And you can do a lot of gas-phase chemistry out in space over a timescale of 10 billion years. Now the other interesting thing is that planet surfaces are bombarded with comets and meteoritic material that are pretty much as accepted, contains pristine matter from the molecular cloud in which a planet and planets and solar systems form. And therefore, when it comes to thinking about origins of life in astrobiology, one has to consider the contribution of interstellar chemistry in providing material which gets onto planet surfaces. Another thing that people don't realize is that when Earth formed, it lost all its early carbon in the form of a methane, CO2 atmosphere, and all the carbon present on Earth right now came from exogenous delivery. Okay? And for meteorites, comets, dust particles, and when we study comets and meteorites, we see evidence of pristine interstellar material. So one can take things perhaps a step further. I'm not going to go into this anymore, but what set early biochemistry on Earth was the existing material, and a lot of that material came from interstellar space. How much did that influence early biochemistry? We don't know. Okay, but let's go back to more practical matters. I do rotational spectroscopy, and in the laboratory, and of course this is all spectroscopy in the gas phase, but it's very precise, 1 part accuracy of 1 part in 10 to the 7th, 10 to the 8th. So one can easily resolve the small splittings we see in molecular spectra, especially when you have unpaired electrons, nuclear spin, fine and hyperfine splittings. And I basically, in my lab, use two simple techniques. One is millimeter, submillimeter, terahertz direct absorption. We go from about 65 to 1 terahertz in frequency coverage. And this is a pretty basic design in concept. You have some gas cell where you make a molecule of interest, you shine radiation through, scan in frequency, and being monitored to absorption by the molecules when there's a molecular resonance with some kind of detector. Of course, in practice, they're a lot more complicated. For my millimeter wave systems, they're based on gun oscillators and Schottky diode multipliers and phase-locked gun oscillators for frequency stabilization. The detector is an indium antimonide hot electropolometer, which we cool with liquid helium to get ultimate sensitivity, and then we do phase-sensitive detection through FM modulation of the gun and use of a lock-in amplifier. We also do narrowband pulse Fourier transform microwave spectroscopy from 4 to 90 gigahertz. Like I said, this is use the narrowband concept, and you probably are all familiar, or at least some of you are familiar with this in the audience. You have a Fabry probe cavity and an air contour arrangement. You pulse molecules in some kind of jet expansion, and you pulse microwaves in. If there's a molecular resonance, the molecules will absorb, and then they decay and emit, and we collect their emission signal as a function of time, the so-called free induction decay, and we take the Fourier transform of that and phase spectrum. So that's what we use in my lab, and we're fortunate, or perhaps not, or unfortunate, that of course none of these systems are commercially available. So if you want to do this sort of spectroscopy, you've got to build instruments yourself. Now we're very interested in transient species, particularly the those containing metals. And these, of course, molecules, they're radicals, or just plain unstable species, and you can't buy them in a jar or in a gas cylinder. And so one of the games we play is how do you make it? And so in the millimeter wave systems, and also now in our Fourier transform system, we have to employ things like AC and DC flow discharges. We use Broida ovens for metal production, and also we use organometallic precursors, anything we can use to make an interesting radical. And there's a lot of experimentation and things you have to do to get this to work. Sometimes things don't always work. That was our first phosphorus source. Anyway, we also often have the search problem because we're looking at molecules where sometimes we don't even know the ground state. We sort of estimate what the rotational constant is based on mass and scaling. And we often have to scan at least 8 times the rotational constant and look for spectroscopic pattern. Okay. And of course, if you have some interesting radicals that have high spin states, you're going to have an interesting spectral analysis. And we deal with that problem too. So in my lab, we have 3 direct absorption spectrometers. Here's pictures of them all. This is my one spectrometer. You can see the bolometer source here, and the optics leading into the cell, the oscillator, the multiplier, the wire grid, and so forth. And this one deals with has a Broida oven attached to the cell for low temperature metals. And here we have another direct absorption system with a cell that can vaporize as things such as vanadium and titanium. And then we have they're both double pass systems, and then we have a single pass system here where we run a longitudinal AC discharge. We can actually use this for velocity modulation and selectively detect molecular ions. And that's one of our bolometer detectors. This is our basic millimeter wave source, gun, and multipliers, which are launched through a feed horn into the free space cells of these systems. We operate about 65 gigahertz up to 1 terahertz or so. And then we have my Fourier transform microwave spectrometer. The original system is 4 to 40 gigahertz, based on a very simple mixing scheme off a synthesizer that goes up to 40 gigahertz. This particular system has 20-inch aluminum mirrors for the Fabry probe cavity. We launch the radiation through quarter wave antennas embedded in the mirrors, collect radiation as well. Our system, we actually angle the beam 40 degrees relative to the optical axis. You lose signal and noise if you do it perpendicular to the optical axis. A lot of people will embed their nozzle in the mirrors. We didn't even want to do that because we wanted to go up higher frequency. We didn't want to launch any weird modes. So we did this 40-degree arrangement, and it seems to work fine, and we don't seem to lose too much sensitivity. Don't think we lose much sensitivity as opposed to shooting the beam through the mirrors. And our machine is all based on a cryo pump. I didn't want to use diffusion pumps because I didn't want oil getting in to the system. So it's based on a cryo pump, and that works actually very well. And that's just a picture of it. It's a big vacuum chamber, and you can see where the angle beam's coming in. That's where we shoot our molecules in the supersonic expansion. And then a few years back, we incorporated a laser ablation source with a neodymium mag laser, and that's just do. It operates continuously across this range. We had to get more higher accurate mirrors, so we made another set of mirrors. They're 7 inches. We weren't sure if we were going to launch the radiation properly into the cell, so we made this plug we could take out and change things. It turns out we didn't need to, but we basically have launched the radiation through a piece of waveguide. It comes out of a hole in the mirror, and we cover that frequency range with 3 multipliers, 2 doublers, and 1 quadrupler, and 2 different low noise amplifiers from Norden and Mimic from J&L, and it works fairly well. So over the years, we were very interested in metal-containing molecules, and here's the list of everything we studied in the lab. The ones with this little red mark are the ones that was the first spectroscopic information ever on that molecule. And you can see that there are lots and lots of ones containing metals, a few phosphorus, and then some without a metal. And we studied everything from hydrides, which we looked at in the terahertz regime, carbides, nitrides, fluorides. Then we get into the monoacetylides, hydroxides, monomethyls, cyanide ones with the cyanide group are particularly interesting, amides, and then some simple molecular ions. And then we've also recently looked at some things that are zinc insertion products, zinc CH3, chlorine zinc CH3, where we've actually found the zinc inserting into the halide carbon bond. They're closed shell molecules. They're not always that interesting spectroscopically, but chemically. And I'm going to talk a little bit about some of the dicarbide. Of course, one can imagine there's many more molecules of this type that one can do, so this is sort of our wish list periodic table of all the metals and all the different combinations. In fact, this table actually sinks way down to the floor with NH2 and CCH and all the things you could attach as a ligand to all these metals. The ones marked in red are the ones studied in our group. The ones in blue are the ones been studied by rotational spectroscopy. You can see the halides are pretty much cleaned up. The yellow ones have only theory. The green ones are optical spectroscopy, and I think the purple is photon electron spectroscopy. And you can see we've just guessed at a lot of the ground states because there's no negative theory on them. So there's a lot of things that could be done and studied in the lab that we have yet to do. Now, in addition to rotational spectroscopy in the lab, I also do another sort of rotational spectroscopy, and that's with radio and millimeter wave telescopes. People say, oh, this is astronomy, we'll stay away from it. But I view radio telescopes as just another form of a molecular spectrometer. So you've got to have a telescope, okay, that collects the radiation. That's all it really does. And of course, we're operating up to as much as 1/3 of a millimeter, and so they have to have a very accurate surface, and the bigger the better. And this is a picture of the submillimeter telescope on Mount Graham, run by us. It's 10 meters, and the surface accuracy consists of panels. There's about 50 panels, and they have aluminum skin on a carbon fiber backing, and they're aligned to an RMS surface accuracy of about 15 microns across the whole 10-meter surface. So you collect the radiation. You have to detect it, and in radio astronomy, we do all heterodyne detection. The signals are very weak. You can't really build an amplifier at 300 gigahertz that's sensitive enough. And so basically you employ mixers, superconducting insulators, superconducting mixers made out of niobium, usually on a silicon substrate. You pull them to 4 Kelvin, you induce a local oscillator, you mix the sky signal with a local oscillator to a lower frequency, 4 to 8 gigahertz typically, and then you amplify with a low noise amplifier, and then you mix down a few more steps and put the signal into some kind of spectrometer backend. And this is a picture of our filter banks we built up with this particular telescope. And the nice thing about heterodyne detection is you have the multiplex advantage, so we, in principle, can collect signal over 4 gigahertz simultaneously. It may not be impressive, but we're looking at very weak signals, so 4 gigahertz is a very nice bandwidth. We can't even take advantage of it because we've got to get the backends. But anyway, and then of course everything has to be run under computer control because you're collecting data, you're on source, you're off source. And so typically our radio telescopes have like 25 computers talking to each other to do all the control system. And so here is a spectrum taken towards a molecular cloud in the galactic center. This is raw spectrum, okay? And any spectroscopist can see where the lines are and where the lines aren't and what the signal to noise is. And so rotational spectroscopy of radio telescopes that does not involve any kind of black magic or special data reduction. To collect the signal, we go on source, off source, we take signal minus reference, and that's it, okay? So if you do electronics right, you can see that the baseline is very nice, and you can get excellent baselines provided you get the electronics. Okay, and just to say, we're very lucky in Arizona that we have our own radio telescopes associated with the university. Sub-millimeter telescope on Mount Graham, I showed you a picture of that not too long ago. It's about 3 hours from Tucson. And then we run 12-meter on Kitt Peak. We took this telescope over from the National Radio Astronomy Observatory in year 2000, and it was aging at that time. Recently, we were very lucky. There was one of these prototype antennas from Alma, which was sitting out in New Mexico. In the end, I got one of them, and we replaced the old 12-meter with this new, fancy, state-of-the-art system at Kitt Peak. And I'll talk a little bit about that later. Anyway, you see that this is simply rotational spectroscopy. Just look at this spectrum here. This is the CN radical, the 2-to-1 rotational transition taken towards the molecular cloud G19.6. The red is the actual astrophysical signal, and the blue marks the lab frequencies and intensities, and you can see you get a nice fingerprint. And that's how astronomy exploits rotational spectroscopy. They can measure these fingerprints in clouds halfway across the galaxy and external galaxies, and they know that molecule is there, and they can say definitively. Yes?
I have a basic question, and if this
Sure.
is going to be too much of a diversion, skip it. We can do it
Sorry.
offline. How does it work? And what I mean is you're heterodyning the signal,
Yes.
but that signal is coming from random collections of molecules all over, so there's no phase coherence among them.
Okay, so
Yeah.
it's not random. Look, interstellar space is pretty vast, and it's not, the filling factor of molecular emission is not, it's like a few percent. So you go to a certain source, okay, you know it's Doppler shift, all right, from atomic lines, and then people usually look in CO, so you know exactly how much to shift your frequency to correct for the Doppler effect, okay, with respect to what we call the local standard address. So we put in Doppler corrections for the Earth's rotation and revolution in the solar system. All this is computed to...
All that sounds fine. It's only the phase that I'm concerned with.
We actually throw away the phase.
But how does the heterodyne work? You have a local oscillator, right?
Yes.
And it's mixing with the signal coming in
Yep.
from interstellar sources. Many, even in some local field of view,
Right.
many molecules,
Right.
they're not rotating in phase.
Right.
So the signals they emit aren't in phase.
Right.
So why don't they cancel when you try to I mean, if I have a bunch of excited...
Okay, we have to take a reference, okay? So we go on source, select signal, we move off source, where there's no signal, and we do signal minus reference. So that gets rid of a lot of the background, okay?
My concern, though, is that for every constructive interference between some emitter out there in space and your local oscillator, there's another emitter whose output is going to be what interfere with your reference. So why do you ever get any net heterodyne signal? I mean, light's coming in for sure. It's only the heterodyning that I'm confused about. The phase coherence must be very long because the molecules keep rotating
Right.
forever. But,
Right.
but of course, it's many molecules producing that signal, I
Right.
assume.
Yes?
And I don't get how their outputs give you some net phase addition, superposition to your heterodyne field, unless they are infrequent enough that basically you have these sort of bursts of signal when you're lucky and at that point.
No, I don't think that's...
Yeah, I don't think so either.
No.
So that's why I'm confused. I mean, when I try to heterodyne something, we do it in our lab. If we don't have a nice phase coherent source, it will not work.
Yes, we have a nice phase coherent source in the local oscillator.
No, that's our oscillator,
Yes.
but whatever it's interfering with also does need to have a well-defined phase, and that's the question that I have. At least that's the way it works, on the lab bench, when we do this sort of detection.
Yeah, I understand what you're saying. I don't have an answer for you off the top of my head.
Okay.
I would, but we can talk about it later.
Yeah, that's a very, I grew with this, so it's like,
Yeah, yeah. No, I know people do this, but I've never quite, I know there's gotta be a simple answer, right?
Like an FTIR works with an incoherent illumination.
But an FTIR doesn't have a local oscillator.
It's phase coherent because it's interfering two beams.
Absolutely.
And it can be the same thing here.
Ah.
If,
Yeah.
if the emission were completely coherent, the signal would be much larger than it
Yeah,
is.
yeah.
Okay,
But
it's
somewhere,
not, but there's still a signal.
yes, but somewhere the signal that's coming in is being interfered with itself, in addition to being added to the local oscillator.
Yeah.
Oh.
One hand.
Yeah, yeah, yeah. Okay.
yeah, please interrupt, because I assume sometimes people know things that they don't. Okay. So, that's just sort of the introduction, and now I'm just gonna talk about a few interesting molecules we studied very recently in my laboratory and then a few astrophysical applications. And one of the types of species we've been interested in lately is these small metal cluster species with the chemical formula MC2. Now, you know from the chemical community that molecules like fullerenes and metcars are of great chemical interest. And then you can add a metal to the fullerenes and get metallofullerenes, and some have the metal inside, and some have them on the outside, depending on whether they're in the first half of the periodic table or the second half, so you can create endohedral and exohedral metallofullerenes. Here's a picture of a very famous one. You have scandium-2C2 embedded in C80, and that's a known molecule. And of course, I mentioned that C60 has been found in interstellar gas. This was not done via rotational spectroscopy, of course. It was done via 4 infrared bands. And then C60 plus, ionized C60, has just recently been identified as a carrier of 4 out of the hundreds of diffuse bands that are present out in interstellar space, and that's in the hollow region. So one might wonder what other fullerene species are present in space, what other fragments of fullerenes. And one notes that C60 is thought to be formed from C2 units, so MC2 is kind of a nice way to put a dipole moment on C2. And MC2 is sort of species of thought to be the building blocks of metal carbon nanomaterials. So of course they had to get nano in there somehow. Okay, but if you look, there are very few spectroscopic studies of MC2 species, and nothing for the 3D transition levels. There's been optical spectroscopy on YC2, that's a 4D metal, and ALC2 by people like Tim Steinle, Dennis Cloutier, and John Meyer. For the 3D metals, the only sort of spectroscopic work is photoelectron spectroscopy, and there's theory by Rayon and collaborators, and they sort of predict that in the 3D metal series, all the molecules, when you put a metal over C2, end up with a sort of T-shaped structure. And there are the various predicted electronic ground states. And we've just begun this work, and so the first molecule we study is scandium, and I'll talk about that in a moment. More about the experimental work. But scandium dicarbide in this T-shaped configuration as predicted from theory is quite interesting spectroscopy, because you have nuclear spin statistics, you have 2 carbons, they're identical particles, you exchange them. And of course, carbon-12 is a boson, and if you want to get a structure, you're going to have to do carbon-13 substitutions of those in fermions. And so basically, yes, because of that symmetry, if it's a boson, the total wave function must be symmetric. If it's a fermion, it must be anti-symmetric, because you have to pair various wave functions, and so as a consequence, you lose a lot of the rotational levels. And then one has to consider the nuclear spin of scandium, which is 7 halves. And so basically, it generates a very complex structure, and you've got to keep track of what levels are there and what aren't. So we didn't just start with scandium. We weren't even sure if we could make these sort of molecules. And so the first project we did was to look at yttrium dicarbide, which had been done, like I said, optically, and there was some MODR spectrum from Tim Steinle, just sort of see if we could make these things in the first place. And we also did the first carbon-13 substitutions on this molecule to get a better structure. And this enabled us to refine the production method for at least a few dicarbides. And what we found critical in making